we're going to verify that our dimension report is correct. So we have collected all of our point cloud on the Features tab because we already ran our program. We moved over to our Characteristics tab. We built all of our characteristics here. How do we turn that into a dimension report? Well, we can come up here to View and come down to Multiple Report. So View and Multiple Report. Hey, look at that. We got a dimension report. Now you notice on our dimension report, the only thing that's on there are the characteristics, because the characteristics are what you care about. I don't care about touching points on the part. You know, if I could just magically put my part on the table and it would tell me if it's good or bad, I would prefer that over having to wait to touch the points. I don't really care about the points. I care about the characteristics. So the characteristics are the things that go on a dimension report. You can remember it like that. Now, first thing we have to do is make sure that every single one of these characteristics is accounted for. But it's kind of not clear what's what when it's just named diameter 1, diameter 2, diameter 3, diameter 4, right? So I'm going to close out of this dimension report. And I'm in the Characteristics tab here. And I'm going to start renaming these features systematically. So I'll double click on diameter 1. And I'm going to highlight the feature name. And I'm going to rename it to something that makes a little more sense. So first of all, which balloon number is that?
Balloon 1.
That's balloon 1. So the first thing I'll start with is B1 and then an underscore. Okay. Then the second thing is, if you were talking to another human, how would you describe that feature to them, right? If you were just talking to another person that had this part in their hand, what would you say? You'd say, look at the bottom left hole, or maybe you'd see, look at the, lower left 375 hole, something like that. So there's some discretion involved with this, but you want a person to be able to find this, right? So it's B1 for balloon 1. And then I'll put 375 lower left. And say OK. And now diameter number 2 is that same B1, but it's 375 lower right. You know what we should probably do? We should probably go back to that first one and call it B1.1. So that way when we name the second one, it can be B1.2. Or you could do it B1A, B1B, B1C, you know, I don't know. But this is B1.2 underscore 375 lower right. So you get the idea, right? So we're making those changes there, and I would do all of them right now. I just don't want to take up a ton of time in this demonstration. I'll go View Multiple Report just to show you, as we're updating those, they are being added to the dimension report. We just have to get it back by saying View Multiple Report. So our next move is we go and update this entire column on the left. We name the features so that way they make sense. Now, if your features, we name your characteristics so that they make sense. Now, if your characteristics happen to be out of order, right? If they didn't go balloon 1, balloon 2, balloon 3, it's kind of annoying from an inspector's point of view. If it goes balloon 1, balloon 17, balloon 33, balloon 2, you're all over the place, and oftentimes you're on a multiple sheet drawing, so you have to flip back and forth from sheet to sheet. So you can actually change the order of these features simply by pulling them in a different order. So you notice now I've changed the order of those first couple features, and I'll go View Multiple Report. And taking a look at the report here, it is now updated to the order that I put them in. So we would rename this entire column. Then we would go back and reorder this entire column so that it's going in order of the balloon numbers. This does not affect how the program runs at all, but it affects how the dimension report reads. Okay, now also on our dimension report, we have a column for measured value. That's what the CMM measured. Then we have a column for nominal value, plus tolerance, minus tolerance, and deviation. Well, nominal value is the size that you want. That's the dimension on the blueprint. Plus tolerance is your upper limit, minus tolerance is your lower limit. Pretty self-explanatory, right? So we're going to go through line by line, and we're going to confirm that every single nominal, upper, and lower limit is correct based on the blueprint. So we're going to confirm that every single one of them is correct based on the blueprint. So for the first one, for B1.1, it should be 375 plus or minus 5. Let's take a look back at our print. There it is. Yep, 375 plus or minus 5. And then we'll go to the next line number and check that, then the next one, the next one. So you get the idea. It's really simple, but you have to go systematically or you will miss something, right? There's a whole sea of details here. Any of them could be wrong. The reason you get paid so much to be a CMM programmer or inspector is you don't let those one or two details get through. You find the one or two details in a sea of details, and you pluck them out and say, hey, this is a problem. You get paid a lot of money to do that. All right, now this deviation column over here is comparing your measured value to your nominal value. It tells you how far off is your measured from your nominal. Pretty straightforward. If it's out of tolerance, it colors it red. It also gives you a graphic readout here where it shows you your low limit, high limit, and how much of your tolerance you're using up. If you're out of tolerance, it colors it red. If you're in tolerance, it colors it green. Simple enough. Right? Basically, update the names, check your nominals and tolerances, and then we have to go make sure that we're not taking bad hits on our CMM. So right now we're making the assumption that the probe that we're using on our CMM has been calibrated correctly, but what happens if somebody comes over and whacks this probe into something pretty hard? I was going to demo it for you, but I don't want to break it. But if somebody drives into that real quickly, is the probe still calibrated? No, it's not. And that's why we have this up here, which is called the calibration sphere. And we'll talk about how to calibrate in the next couple of weeks. But it's not, we can't take it for granted that that probe has been calibrated. And oftentimes, your dimension report will come out all red. And you're like, whoa, what's going on? This part's bad. Then you do a probe calibration. You run the exact same program again, and your part's magically green. Everything's good. Because your probe was miscalibrated. The machine thought it was a different size, right? It's common, especially, probes get dinged or whacked or whatever. That certainly can throw your data off. So the point being, we need to systematically verify that each one of these measured values is correct. So we already systematically verified nominal off the print, upper and lower tolerance off the print. For measured value, you have to actually measure the part. So the first one we have is B1.1, 375 lower left. It says 382.2. That's what the CMM says. Well, that's talking about this hole right here. It is plus or minus 5, so dial calipers is fine for that. So I'll measure this with dial calipers. And I am getting 384 thousandths. 384 thousandths. And the CMM report said 382.2. So is the CMM giving me a good value? I don't know. You kind of need a rule of thumb to help you out with this one, right? Because if the CMM said 382.2 and the calipers said 382.3, yeah, the CMM's obviously giving you good results. That's within a couple of tenths. Of course you're going to have measuring error with calipers, of course. You can't see tenths with calipers anyway. Well, so essentially the CMM said 382 and I got 384. Well, that's 2 thousandths difference. What's the total tolerance here? Plus or minus 5. So 10 thousandths is the total tolerance. So we're 2 thousandths off, right? CMM measured 382. We got 384 with calipers. That's 2 thousandths total difference. Total tolerance is 10 thousandths. So we're using up about 20% of our tolerance. The rule of thumb is, if you're matching within 30% of the total tolerance, you got a good CMM program, most likely. You're never 100% sure, but most likely. So this is called a manual verification. We are manually verifying that the part matches the measured value on the CMM. So manual verification. We're manually verifying that the dimensions measured with calipers match what the CMM measured. You also want to make a note. I said this loosely. I said the dimensions you measure with calipers. What if you have a plus or minus 1,000th tolerance? We have a couple of those. Can you really use dial calipers to verify if you're within plus or minus 1? They're not really precise enough. So you have to select the appropriate gauge based on the tolerance. So plus or minus 5, calipers are fine. Plus or minus 3,000ths, I don't really trust calipers that much anymore. Maybe you want to use a micrometer if it's an external dimension, or a gauge pins if it's a hole. Plus or minus 1,000th on a hole, you can't use calipers. There you'd probably be using either Deltronics gauge pins, which go down to tenths of a thousandth. They're super precise, very expensive, or a dial bore gauge. So you have to select the correct gauge based on the tolerance. Now the flip side is, if you have a hole that's plus or minus 5,000ths and you're using Deltronics pins, that's way overkill. You're going to waste a ton of time. You're probably going to reject parts that are actually good as well. So you want to select the appropriate gauge based on the tolerance. Rule of thumb: CMM measured value has to match the hand measured value within 30% of the tolerance. That's my rule of thumb. Right? If you're using up half of your tolerance, I have something's not repeating. You're missing something.
So you said CMM value.
CMM measured value matches the manually measured value within 30% of total tolerance. So we would go through this entire column systematically, make sure everything matches. If it does match, you can be pretty confident you got yourself a good program. I would continue to do the manual verification on the next part or two. So you've manually verified like 2 or 3 parts by that point. And if the results keep matching what the CMM says, you probably have a good CMM program. All right. After all that, we now have a good CMM program. We want to save this and submit it to Blackboard. So we would do a file, save as. We would do our last name, dash first initial, and then an underscore, and whatever the assignment name is. We just copy the assignment name right off of Blackboard. And we'll go to the downloads folder, and we'll hit save. So that saves all of the files that drive Calypso. You'll notice that Calypso's screen goes black, and then up here at the top, it renames your file, whatever you just named it. So we're now operating on the new file. As we get going here, I'm going to have you run production runs, small production runs on like 5 parts, maybe 10 parts. So I want you to save your dimension reports on those 10 parts, because I can really quickly look at your dimension reports and see if you have a good program or not. So how do we save a dimension report? Well, we go View, Multiple Report. It's funny. Right now it says it has no results available. So I just reran the report in the background, but I didn't clear the existing results, so it took the results it had and just dumped them in there again. You will have to do that if you save your file under a different name. It loses your results. Okay, so here's my dimension report. This is not engraved. Oh, it is. Okay, so it has 1 on it. For the text, in this field right here, I can type in the text. I'm going to put 1 because that's what it says on the part. And then I'll go File, Print, and I'll say Export as PDF, and then I'll click Print. And I'll go down to the Downloads folder, and I am going to name this as whatever the lab name is, and then an underscore, and Part-1. The reason I added Part-1 there is because this is Part 1, but I'm going to inspect 9 other parts. So when I do the second part, it'll be whatever the assignment name is, underscore Part-2, etc. All right, so I'm saving that dimension report. Let's say I swap out this part. And I now want to run another program. I want to run the same program, but on this part. What do I do now? Well, my dimension report is saved, so I can close that out.
So
I want to rerun the entire program, but I don't have to program anything anymore. I just want to run it. Well, I'll come to the features window. Click on the top, hold shift, click on the bottom, hit run. Do you think I should clear my existing results? I have to, because all the other results, all that point cloud I had was to a different part. That part's gone. So I want to inspect this part. It's a different part. I have to clear the results. How about for our selection? What type of alignment should we do? Manual, current, or named? Named. Now you notice that that has been named whatever I saved the file now. It's not measurement plan 1 anymore. It's whatever this file is called. That's why they call it the named alignment. The bottom line is, it doesn't matter what it's called. It's the third one down in the list always. Pick the third one down in the list. We can do all characteristics or current selection. In this case, it actually makes no difference. All characteristics reads through the characteristics list and probes as many features as it needs to get those characteristics. Current selection is going to probe everything that you have highlighted. In this case, it's 6 of one, half dozen of another. But we'll learn later there's quite a bit of power to this. And when you get complex programs, this can help you to really improve your efficiency a lot. A safe option is current selection. That way, it's just going to probe whatever you have selected. All right, for order of run, we're always going to select feature list. For speed, we'll go 55 and start. And there we go. It's off and measuring the part. Now, for the first couple of runs of this program, I would keep my hand on the speed dial because there may be something about the program that you didn't catch that's wrong. Once you've run it like 2 times, you can crank this speed all the way up and you can walk away from the machine. That's the beauty of a CMM. Okay, once this is done, I'm going to save this updated dimension report as a PDF. It'll be whatever the name was, -2 instead of -1. And then I'm going to submit all my files to Blackboard. Now there is an SOP out on Blackboard that shows you how to submit the files. Basically, you're going to submit the entire folder that's used to drive Calypso. That folder is called, in this case, minor T assignment name. So we're going to submit that entire folder, but as you know, you can't submit a folder to Blackboard. So you got to right click on it and say send to compressed zipped folder. Now you notice I did not put the PDF dimension report in that folder. I want the PDF dimension reports to be outside of that folder on purpose, so that way they host directly in Blackboard. My thinking on that is when I go to do grading, I can look at your dimension reports and I can really quickly tell if you did the assignment correctly or not. Now if you did it correctly, I want to give you 100. Right? I assume everybody's doing their work and they're understanding it. But occasionally you get some weird results and it's like, oh, this person really doesn't understand this. Let me find out why they don't understand this. So I can see that from the dimension reports. If I can see you don't get it, I'll download your program. I'll extract it, I'll open it up in Calypso, and I'll find what the problem is and I can give you better feedback that way. That's why you give me the file that drove the machine zipped, in case I need to go investigate, and then you give me all of your loose dimension reports outside of that, so I can grade them quickly. Does anybody have any questions? So a lot of what we saw today also applies to the previous assignment, which is block 1. Now in week 6 and onward, you're going to start having lectures that shows you how to inspect this part and has you write an offline program for it. And then you're just going to come in here and you're going to run your offline program. So this is the end of the live lectures during lab. This is the last one here. But this has shown you everything that you need to know to inspect like 95% of basic parts. So what you saw with modifying the dimension report to add balloon numbers, what you saw with manual verification of your parts and rerunning parts afterwards, all of that applies to block 1 and to this. Now, because we're going to be transitioning to, let me do a sidebar here now that this is done and save my dimension report. How do I save my dimension report? View, multiple report. That'll pop it back up on the screen. For text here, this is now part number 2, right? We'll go File, Print, Export PDF, Print. We'll grab the same name that I had before, except now it's -2, and we hit save. When we go to submit on Blackboard, we'll grab our whole folder, send it to a zip folder, and we will attach 1, 2 PDFs and the zipped folder. PDFs are separate from the zip folder. You're going to have to hit Browse Local File 3 times, or just select them all and attach them all. So if we were only running 2 parts for production, you would end up submitting 3 files. You'd submit the 2 dimension reports loose, submit the 1 zip file.
So today we're doing 2 parts?
So let me stop the video here.